that melts, it's like green.
Exactly. Yeah. You know, I'm going to give some examples of maybe like you know, sort of expected by everyone.
Oh, yeah.
Yeah, I'm gonna say that.
Exoplan makes the relation between
You still have your thing downstairs?
between
good.
the patient
Yeah,
breath
that's
and the
right.
planetary atmosphere.
They
So.
let you stay there?
I don't know. They have a meeting with,
The space and location people?
those two, because the whole group at least met with Mrs. Payne.
Yeah. Did that go well?
I don't know.
Everything is changing. Everything is changing.
Yep. I mean, I know you were working.
I have a picture. Barbara Bell was in the office. Picture of her.
Yeah, it's like a regular meeting.
Work
So, so company doing this.
Yeah, I can't get to the
I was through, releasing the ice cream, it was all right. They know their way around the parents.
Oh, yeah.
I don't think that we need it just yet, but yeah, I think
Yeah, we can close the blinds down.
blinds. No. I would wait until people finish coming in,
Contrasted enough,
and
right?
then we bring the blinds down.
Yeah. Okay. Sounds good.
You really need, so I'm just, okay, I give you for now.
I think it's okay. I think it's contrasted enough. Yeah, we don't need probably, right? Only if the sun comes out. Yeah.
Right, yeah.
In a.
Have you got the microphone?
Yeah.
Go ahead, okay.
It's on already.
So Nelson says to wait a few more minutes just to let people finish coming in,
Yeah.
and then we'll just go ahead.
Okay. Hello. Oh yeah, I just did. Yeah, I think. Can you hear me? Should I be closer?
So I think that we will wait 2 more minutes just to let people come in and get coffee and sit down and.
I was going to check if the clicker works. Oh yeah, it works.
Oh, yeah, let it go. That we're reading tonight?
No, that's Gran Gusto, I think. Yeah.
You know they used to have the scanning telescope editorial office in the same building,
Yeah.
but then now they moved to Harvard Square.
Oh really? I didn't know that.
But it used to be same building.
All right. I did not know that.
Well, it seems that there's nobody else coming in, so. You ready, Jen?
Yeah.
Okay, well, thank you everybody for coming to today's CfA Colloquium. It is a pleasure for me to introduce one of our own, Iouli Gordon. And just as a very brief introduction, Iouli got his bachelor's degree from the Institute of Physics and Technology in Moscow, and then went on to Canada, to the University of Waterloo, to get his PhD and in physics. And then after that, he actually came here 17 years ago. So he started here as a postdoc, and Iouli is a perfect example of how you just go up at the CFA, right? It's like he came here as a postdoc, he never left. And, and then right now, Iouli has been the director of HITRAN since 2017. And he's also the chair of the International HITRAN Committee. And he's also our new division chair for the Atomic and Molecular Physics division. And you know, I don't know, especially the younger people in the audience, I don't know how many of you actually know of HITRAN, but to me, HITRAN is a gem that we have on the first floor. It's like, you know, anybody in astronomy who uses line lists, that's where the line lists are coming from. And you know, I appreciate so much, you know, every time I need to know something about the line list of any molecules, you know, I can go downstairs and ask Iouli, and he's an endless source of knowledge. So thank you, Iouli, so much, and we are looking forward to your presentation on HITRAN and HITEMP.
Thank you, Mercedes. Hi, everyone. It's a real pleasure to give a talk about HITRAN. Again, it's has been here 17 years, and I really happy that this opportunity finally came. But I would like to say first that I'm very honored to direct the project that's actually much older than I am. So HITRAN was incepted in the 60s. And the original goal of HITRAN was actually military. And it started in the Air Force. And the original goal was to subtract the atmosphere from observation of thermal emission from enemy airplanes. And in fact, the very first shot basically at this atlases of spectral lines was done for water vapor, and you can see it was in 1964 by Bill Benedict. And if you use HITRAN, you would actually notice that the format of it is already very close to what we're using to this day. And of course, we added so much parameters since then, but that's I'm going to continue about it. So what would we consider birthday of HITRAN as it is now is actually exactly 50 years ago. So we shared the birthday with the CFA, or birth year, I should say. And it was a report that when also Larry Rothman, the previous director of the HITRAN database, got involved in a project and eventually took it over. And under Larry's direction, it went from paper atlases and hard copies to punch cards, then to magnetic tapes, then to the CDs. And this is HITRAN 96. That's actually when the project moved to our institute, so to the CFA from the Air Force. And then we were distributing the database through FTP. And now our website is hitran.org. We have very dynamic, modern structure. You can browse the data. You can download it in different ways. And the flexibility of data increased substantially over the last 50 years. I'm going to first just give you a heads up of what I'm going to talk about because we have different aspects to the database. The most popular part of the database is a line-by-line compilation, and that's where we'll talk in most detail. We have also absorption cross-section. So for the molecules for which we cannot yet construct a good line list, and that relates to some heavy molecules or any molecule with low line vibrational modes that are populated even at terrestrial temperatures, and therefore the density of lines is very high. We just provide experimentally determined cross-sections, so basically intensity versus wave number, or wavelengths if you want, and at different pressures and temperatures, so the scientists can interpolate. But this is, of course, much less flexible format than the line lists provide. But we have about 300 molecules parameterized this way. We have collision-induced absorption. I will mention about it in more detail. This is something we added very recently. It's a so-called water continuum. And for 50 years, we were avoiding adding it to the HITRAN database, and both Larry and I were very reluctant, and I'll tell you why, and I'll tell you why now, because I'm not actually going to go into many details. So water continuum is something that is very still poorly understood completely from the physics point of view. So there are three factors that contribute to it. One is collision-induced absorption between water molecules themselves and with nitrogen and oxygen atoms. The other one is underlying water dimer. So under some of the lower temperatures in terrestrial atmosphere, water actually forms a bound water dimer complex, which is very hard to do line by line. And finally, because water lines in the terrestrial atmosphere are so strong, their far wing contributes to absorption substantially. It's actually sub-Lorentzian, so we usually cut off, when we calculate in the terrestrial atmosphere, everything 25 wave numbers after the line center. But in case of water vapor, you cannot actually do it, so it's a substantial absorption beyond that. But since we don't really know much about far wing, we cannot really model all of these three components together properly. And experimentally, it's very difficult to disentangle. So we just this empirical model from scientists from AER. Eli and Lover is leading this group, and they actually maintain this part of HITRAN. And we were reluctant about it for so many years, but pretty much after every talk, we would be asked, when are you adding the water continuum? And the final draw was I went to this very hardcore atomic and molecular physics conference, and I was given this talk, and then suddenly the person who was all his life calculating the dysprosium atom or stuff like that suddenly asked, when are you adding water continuum to HITRAN, which I thought was very strange, but if he needs water continuum, then we really should add it, and we contacted our colleagues at AER, and it's part of HITRAN now. In fact, again, as I mentioned, we just added it less than a year ago, so it wasn't even an official HITRAN 2020 release. Aerosol properties is another part of HITRAN that we actually do not develop themselves. Steve Massey from University of Colorado maintains this part of the database for us. The high temperature analog of HITRAN, I'm going to go into more detail later on, because it is very relevant to the atmospheres of stars, brown dwarfs, and the exoplanets, which of course a lot of scientists here in this room are interested in. We have this HITRAN application programming interface, which I'm not going to talk about a lot, but you will see the power of it through this presentation when I'll be comparing different spectra with the ones simulated from HITRAN using Happier. But it's basically a set of Python libraries that can allow you to download the data efficiently and do many different calculations, transmission, absorption, emission, you name it. And then we have this supplemental folder where we maintain different auxiliary files to HITRAN, for instance, total internal partition sums, so which are required, for instance, if you want to calculate spectra at different temperatures. Again, we have Twitter, or X, if you say now, and then we have YouTube tutorials if you want to follow through the database. And oh yeah, this is actually outdated. We now have almost 30,000 users, so in 2 weeks we'll have 30,000 users registered in the database. And this is just under this new structure, which we released just a few years ago. Again, I'll be coming back to different things here through the presentation. Now, of course, we're all fortunate that HITRAN has a lot more peaceful purposes now, and the whole set of NASA Earth observing missions rely heavily on HITRAN. Of course, this is slightly outdated. You see Tempo is a proposed mission here, but we know that thanks to our friends on the first floor, it's actually up and running. And of course, there are so many so many satellites that are equipped with the spectrometers that do use HITRAN. And just some of them, of course, are shown here, and they have many different instruments and different wavelengths, and they all do rely on HITRAN. In fact, majority of our funding comes from support of the terrestrial remote sensing missions. And I just showed you only NASA missions. and there are so many European missions, Japanese missions, Canadian missions that also, of course, rely on HITRAN. Now, I'll talk about some other sensing methods. This is also satellite observation. So if before you saw all the spectrometers measuring reflected sunlight from the surface, so basically measuring atmosphere through its all bulk, absorption of reflected light from the surface. There is also solar occultation method. So there are satellites that are, for instance, this Canadian satellite ACE, atmospheric chemistry experiment, that goes in orbit around the Earth and basically constantly looks at the sun and probing different layers on the top of the atmosphere. And it operates in infrared. There are a lot of ground-based spectrometers that basically also just look at the sun. And there is this network called TICON, which has different locations all over the world. And they measure the full absorption of the atmosphere of the solar radiation. Again, they very heavily rely on HITRAN. There are still airplane, of course, based measurements, balloon-based measurements. So yeah, it's referring to recent events. And in fact, you all know Caroline Nolan, who is in a Tempo group. And when she was doing her PhD in Canada, they had a balloon that flew away and put to shame the Royal Air Force. When it flew to England, it took a very long time to shut it down. So these things, and it was purely scientific balloon, as far as we know. And of course, the last thing about the terrestrial atmosphere, which is of course important to all of us, HITRAN is a backbone of all climate and radiative transfer models, but we make it so simple and accessible that there is so much of this do-it-yourself radiative transfer models. If you look for HITRAN on Twitter, which I once made a mistake to do, it's a very heated discussion, and there are both parts of political spectrum use or misuse HITRAN actively, and it's sometimes overwhelming just to look at it, and it's yeah. So we're not going to go there. But again, that's great that the HITRAN, which is a free database, enables everyone to make these calculations, whether correct or not, but we make it accessible to people. Now, there are so many different, very interesting uses of HITRAN. And basically, HITRAN is used everywhere where light is being absorbed in a gaseous medium. But this is one of the exciting uses. So it's actually a patient breath analysis. So there are a lot of laser systems now built to specifically target molecules that are traces of different diseases. And this is like a very small part of a table which enhancement of different molecules and patient breath is responsible for, is an indicator of different diseases. And there are also not just molecules themselves, even isotopic ratios of some molecules can give you ideas of different diseases. So that's why we're actually very careful about our isotopic ratios. So this is a very active research field. But I'm just going to smoothly transition from here to something that is more interested, of more interest to everyone here. So there is this molecule, carbon disulfide, which we didn't have in HITRAN before 2020. And as you can see, it's a trace of schizophrenia, coronary and artery diseases. And we collaborated with scientists in the University of Central Florida, Konstantin Vodopyanov. So Konstantin got a grant from National Institute of Health to measure CS2 specifically as a tracer of schizophrenia and coronary diseases. And they measured it, but they didn't have expertise to analyze it, so they called us. And Ekaterina Karlovets, who was a postdoc here at the time, analyzed their spectrum. And also we found out that in stars there was data that was previously actually used, and it was just nowhere near where it's supposed to be. And we decided not to stop there. We analyzed this little band, which is actually by far not the strongest band of CS2. So Ekaterina collected all the experimental data that was available and fitted them together to the semi-empirical model that actually worked really well. This is a line list, or I should say cross-sections calculated with a line list that she created versus PNNL. Cross-sections of PNNL is basically a database of this experimentally determined cross-sections, very carefully under very well-controlled laboratory transitions. And you can see agreement is quite good, and of course we go beyond of the wavelength range that PNNL could cover, and we published the line list, added it to HITRAN, and just a couple of years later, CS2 was found on Venus. So it's important to understand that we spectroscopists we find different sources of funding and trying to piece things together and put in databases, and then for everyone's benefit. And this is probably what I will say a little bit at the end about the funding issues. So we have to be very creative. And okay, so this particular spectrum was where CS2 was determined was done with Venus Express. But I think everybody knows that there are so many planetary missions that also rely on HITRAN, including ExoMars or Cassini. And of course, you saw Julian's David talk last week, and so many people here already involved at the WST, for instance, is very heavily relied on the HITRAN data too. And I actually find this is very exciting time for HITRAN. So that's in my mind how WST spells out. So it's a great time to collaborate with colleagues here and across institutions. I'm mostly going to be talking about planetary atmospheres, but I did want to mention that the WST recent results from protoplanetary disks shows us beautiful spectra, and they're very beautifully fitted with HITRAN. And again, this is, but they also identify some missing features, and this is area of science that we really never tapped into. So I really want to talk with scientists here about some ideas of potentially applying for funding to improve HITRAN for protoplanetary disks and similar objects. Now, since inception of HITRAN, we release quadrennial editions. So the most recent one is HITRAN 2020. We have 88 authors, but in reality, the HITRAN community is so much larger. This includes scientists who measure spectra, who calculate spectra, who validate it against atmospheric or planetary spectra. So it's a large community, and we really invite everybody to participate. It's much easier to do it together. Just a little bit of bragging. The citations to the HITRAN editions are very high. This is a citation of every of last 6 HITRAN editions per year. And you can see that with every new editions, the citations per year increase. And this is because we improve the quality of the parameters, we add new molecules, new bands, and the user base, of course, also increases. And unfortunately, only 10% of scientists who actually use HITRAN cite it. So you can see that this basically thousands of citations in reality could be substantially more if everybody followed standards for citations.
How do you find that number?
So this is from Web of Science, so you can actually see.
The ones that don't cite you.
Sorry?
The ones that don't cite you.
Oh, okay. So
You read the paper.
well, so the thing is that there are many black box codes that integrate HITRAN in. So I know that code was used as like, and again, many of you may be using HITRAN every day, and you may not even realize it because it's embedded into the different codes. So, yeah, and I didn't put the 2020 because it came out just in 2022, so it doesn't have enough. So again, going back to the HITRAN data itself, so the line-by-line data have many parameters, but the major parameters is basically position of the line in a energy domain, its intensity, which is basically an area under the profile, the broadening, Lorentzian broadening due to collisions with the ambient gases, and the shift of the spectral line, again, due to collisions with different gases. But in reality, we now have so many more parameters, but these are the fundamental parameters that are underlying the line-by-line edition. So we in a line-by-line section, we have 50 molecules, and each of these molecules, or majority of these molecules, we actually have multiple isotopologues represented as line lists. And here is basically how we went from HITRAN 2016 to 2020. So the molecules in bold are those that we updated with respect to the previous editions. And in parentheses, you see, oh, sorry about that. In parentheses, you see isotopologues, and basically if they're in red, that means we added isotopologues to a certain molecule, and we added a bunch of new molecules, including this CS2 that I already mentioned. Now, we're trying to combine the best of several approaches here. So we're trying to be practical, and HITRAN is basically a flagship in this sense because we set up certain parameterizations many years ago, and we showed the field how to use it in a proper way. And whenever we change or add something to HITRAN format, it's done in a close collaboration with atmospheric or planetary community. So the parameterizations actually are very well thought through. And I also will mention that when it's a very large line list, how we solve this problem to be more practical in the HITEMP examples. Of course, the accuracy is very important. And again, I was just kind of relative what is important more for terrestrial atmosphere for astronomy. So the accuracy might be a little bit less important in astronomy, but it still is important. For instance, if you do cross-correlation measurements in exoplanetary atmospheres, you actually need to know the line positions of individual lines very well. But when you do GWST retrievals at low resolution, you don't really need to know line position extremely well, right? So it's always a trade-off. And then again, completeness. Of course, for astronomy, there are so many different applications, and there are a lot more molecules. You need more temperatures, more isotopologues. So completeness is a little more important than terrestrial atmosphere. And then traceability is something that seemingly is not important to anyone, but it is very important to us. So we actually keep very, and I'll show a little more about this precise track of where each parameter is coming from, and enable citation not only to the database but also to the original sources. So it helps us to maintain the database because we know where we took things from, but it also credits the original data providers. So we also have a certain scheme how we construct the data, and basically we take data from different sources. We compare with previous edition of HITRAN, compare them against each other. We check the parameters if they're within their physical boundaries. There are so many different little checks that we do, but it may seem a little boring. But anyway, after all those checks, we also compare with the raw laboratory data if we have it, or with field data, atmospheric data, or even in some cases planetary data. And then we discuss all of this with the HITRAN committee, which is consisted of about 20 scientists, spectroscopists, atmospheric scientists, and planetary scientists. And then we put it to HITRAN. And this is the most important part of the HITRAN development, is delivering the data to users and receiving the feedback from users. So it's a very important part of HITRAN. So if you feel you can contribute to HITRAN, or you think you found an error, please don't hesitate to contact us, because it's, again, as I mentioned, a very important part of the development of the database. This is the example of, again, when we talk about completeness of the database. So every new edition, we add more bands, more isotope logs. So this is a perfect example of SO2. So we had only these bands in HITRAN 2016, but we added so many more in the next edition of HITRAN, and we also added new isotope logs. But it's that's completeness. But we, as I mentioned, we of course also worry about the accuracy, and we compare the different sources of data against, again, this PNNL spectra, which is a raw experimental spectra, but it's under well-controlled experimental conditions. And you can see that if you check the residuals, and we calculate the cross-sections to compare with HAPI, the HITRAN application programming interface that I mentioned before. So you can see that the HITRAN 2016 actually had a rather appreciable residual when compared to experimental spectrum. And then there is this data, which is largely ab initio line list from NASA Ames. And you can see, like, in a core of the band, it actually had a pretty good agreement, but not so much on the wings of the band. And then there is this another empirical list from Olga Naumenko in Tomsk Institute of Atmospheric Optics. And you can see that in this particular case, Olga's data was the best when compared to experiments, which shows it, again, for this particular band. But it doesn't mean that in other bands it was exactly the same story. We actually have to go band by band and make these decisions. Now, I did mention that we need more accuracy in the terrestrial atmosphere, and actually we needed to a point that some of the remote sensing missions want to know certain parameters to 0.3% accuracy, which is when HITRAN was incepted, was absolutely even unimaginable. So to go to this accuracy, we actually cannot use void line shape anymore. We have to use more sophisticated line shapes. And we actually did introduce these line shapes to HITRAN. So thanks to work of Robab Hashemi, who was a postdoc here a couple of years ago, we developed complete data sets of the speed-dependent void profiles by adding substantially more parameters. And you can see in an example of CO that with including these parameters, the residuals drop. And of course, we had some similar stuff for some other molecules. And what is, of course, very important for the community is CO2, because there are several missions now, US missions and foreign missions, that measure CO2, and they're not necessarily measuring in a thermal infrared, where CO2 is most important for climate. They use near-infrared bands that are easier for different reasons to measure from the satellites, and they all place even harsher requirements. So now they want 0.1% on certain parameters. So it's we try. So we basically Robab collected all the experimental information and went through it very carefully and removed outliers and built this semi-empirical models, which are in red lines here. And in fact, by just looking carefully at available experimental data, we were able to change some of the theories which were somewhat misguided. For instance, this temperature dependence of speed-dependent parameter of this particular profile. It was thought that it has the same temperature dependence as the main Lorentzian width. But in fact, that's not true. And we basically see it in experimental data. And the red model went to HITRAN, whereas scientist previously was using this temperature dependence, which was simply transferred from Lorentzian with temperature dependence. And again, when we go through all of the sophisticated models, which are all now in HITRAN, you can see the reduction of spectra, sorry, a reduction of residuals when you compare with experimental spectra. Now, I did want to address certain misconceptions that I think exist here, because sometimes at a coffee, I'm being asked, how's it going in your lab? So there is a misconception sometimes that all of our data is experimental. Or on the contrary, there is sometimes misconception that it's all theoretical. So, so we use both, basically. And why we use both? Because both approaches have their advantages and disadvantages. Advantages of using experimental data. So when you actually measure everything in a relatively unblended spectrum and resolve all the lines, you actually can get very good parameters. You directly observe any quantum mechanical effects that not necessarily easy to determine in oversimplified theoretical models. You can so it is definitely very powerful. But again, when lines are weak, or you have overlapping lines, or on the contrary, you have saturated spectra, it's impossible to get good parameters. And then you may have impurities in spectra. For instance, yesterday we had the ammonia task group, and basically ammonia is so sticky that if you once put it in your experimental cell, it stays there forever, basically. I think it was a span of like 20 years or something, which is something absolutely ridiculous. So, so you do get impurities. And of course, you cannot buy a new cell for every gas. So there are impurities in experiments, and one has to be mindful of that. Sometimes it's not that easy to control the conditions. And then it's not easy to cover a large spectral range and at the same time measure a large dynamic range. So for instance, the technique which is Fourier transform spectrometers, they and the spin and L spectra, which I show are Fourier transform spectra, you can simultaneously measure very wide spectral ranges, but you cannot probe very weak intensities, whereas cavity ring down spectroscopy technique allows you to measure very weak intensities, but you cannot really do wide spectral ranges. And this is some examples of when we deal with experimental data. This is some collection of water vapor lines broadening by air measured in different laboratories. So this laboratory is just numbered. So you can see that for every 4 of this sample of lines, the broadening measured in the laboratory 21 substantially differs from the measurements from laboratories 4 and 12. And of course, you don't want to take an average in this case. You just disregard the 21. But then you often have cases like this. So here, for this line, measurements in laboratory 18 and 14 agree very well with each other, but not with laboratory 13. And for this line, it's the other way around. So it presents a very substantial challenge for us. And we actually do end up often looking at this individually. And there are thousands and thousands of lines of water, and thousands important lines of water, and there are tens of hundred thousands of water lines in general in HITRAN. So we have to be mindful of that. And of course, theory is a nice alternative. What theory can offer you is completeness, so you can basically predict lines that you cannot easily observe by experimental methods. You can adjust the theory to basically match some of the high quality experiments. But again, still, especially for line positions, theory or broadening theory cannot really compete with experiments. Sometimes the models are found to be oversimplified. And then there are semi-empirical methods which we often use too. So when you feed the experimental data, you feed it to things like polynomials, which basically beyond the experimental range of your feed can really go crazy on you. So So there are difficulties with all of those approaches. So we are basically trying to combine the best parameters, and to us it doesn't matter whether they are calculated or measured. So the HITRAN is really a combination of different parameters. Now, since there is a lot of interest of finding oxygen in exoplanets, I would talk a little bit about it, because we actually have calculated very good spectrum of oxygen here, and also for different terrestrial missions we do worry about oxygen too, believe it or not. And so just kind of an overview of the three lowest electronic states of oxygen. I'm just putting one vibrational level per electronic state. But you have this X triplet sigma ground state. You have the next electronic state is A singlet delta, which corresponds to this 1.27 micron band. And there is this singlet sigma state above it, which corresponds to this 0.76 micron band, which is also called A band. And of course, the transitions between these two states and the ground state cannot be through electric dipole, because oxygen is homonuclear. But these transitions are possible through the magnetic dipole and electric quadrupole mechanisms, and the transitions between these two states is possible only through electric quadrupole mechanism. And in general, if you read the textbooks, magnetic dipole transitions are much weaker than electric dipole, and electric quadrupole are even much weaker than magnetic dipole. But there are exceptions to this, which I'm going to show. So the A band is very popular in remote sensing. And why oxygen is very popular in remote sensing at all is because it's so uniformly mixed in the atmosphere that when you try to measure other gases, you actually calibrate against oxygen, because you know everything about oxygen, and definitely it's the fact that it's uniformly mixed helps to remove systematics from your real spectra. So the A band is actively used by several remote sensing missions. From spectroscopic point of view, it's substantially simpler than 1.27 micron band. It has only 4 strong magnetic dipole branches versus 9 in 1.27 micron band. And the reason for that is that, again, because oxygen is homonuclear, and the nuclear spin of main isotope of oxygen is 0, so every other rotational level is not populated. And when it happens in the singlet sigma state, you basically reduce amount of possible transitions to just 4 branches. It doesn't have strong underlying collision-induced absorption, and electric quadrupole lines are very weak. And in general, it's much stronger absorption. And another thing is that it doesn't have a substantial air glow, and I'll mention this a little later. But it does have certain disadvantages, because the remote sensing missions, which I mentioned, that measure CO2 or methane, they are all in near-infrared or infrared. So the A band is really far from them. So therefore, this removing of systematics is somewhat questionable, because in an energy spectrum, it's quite far. So, and another thing is that it's actually, because we have so much oxygen, and A band is very strong, it's saturated. So in fact, in a GOSAT spectra, the R branch is completely saturated. But at the same time, the METHANSAT, which is a mission that is being developed here, and microcarb, which is a mission developed in Europe, did decide to look at what if we just try really hard and get spectroscopy narrowed down and use this 1.27 micron band, because it does offer advantages. So we looked at the air glow first, and Kelly and Chong has this brilliant postdoc, Kang Sun, who's now a professor in Buffalo. So we looked into it, and basically, when I was working with Kang on it, I realized that this blue model, which was used by everybody, not just the group here, is based on a HITRAN line list, but without acknowledging the fact that the HITRAN formalism is developed for local thermal equilibrium. And the air glow happens due to the fact that after photochemical destruction of ozone, the oxygen is already formed in the singlet delta state, and then it emits down to the ground state. So you basically start with excited state, so you're not thermally populating it. And just by adding these wavelengths to the lower state energy, you can actually correct the model completely. And this is a Skiamaki spectrum. Skiamaki is also a European instrument, satellite instrument that looks down at Earth and measures different gases. And it does measure air glow. And this is a real atmospheric spectrum. Just to check that nobody is sleeping, can you tell me why we don't see absorption here, the oxygen absorption? So it's a night glow. So the satellite measures the reflected sunlight during the day, but it also can look during night, and that gives us uncontaminated picture of the air glow, and that's why we can model it nicely. So we got it working really nicely. So okay, so air glow is not a problem anymore. Well, let's go further. So in 2010, I was contacted by Jeffrey Toon, who is a scientist at JPL, and he was measuring with a stick-on spectrometer absorption of entire atmosphere. And after subtracting all magnetic dipole oxygen lines, he realized there's some leftovers. And he knew it is oxygen because by changing at what time of the day he's looking at the sun, he can see that the depth changes, and knowing the other properties of oxygen, he can trace it to that. And we figured out it was electric quadrupole transitions. And I actually contacted Samir Kasi and Alan Kamparg, who do experimental measurements, and they measured a couple of those transitions in a lab, and then we built a model, and then it was able to simulate. But it's still by far not perfect. And the part of the problem was that the magnetic dipole lines was actually based on some not necessarily most accurate measurements. And then when we did model the electric quadrupole transitions, we modeled only the ones that you can very easily see here, the ones with delta J equal 2. So the selection rules are different from magnetic dipole ones. But there is also transitions that overlap with magnetic dipole ones, and we didn't try to disentangle them. And apparently, later on, we realized that the model we used here was slightly oversimplified. So just to address this, the magnetic dipole transitions were really remeasured accurately in NIST and Grenoble. There are several papers publishing some new measurements, and we feed them all together. And here I'm going to talk about only intensities, but we did do line positions as well. And just to give you some quick background, so the triplet state has two omega, or actually three omega components, the 0, plus and minus 1, and the upper state has only 0. So basically, what happens is that although it's seemingly on an energy scale, the states are very far from each other, they're actually mixed. So omega 0 component from a ground state is mixed with omega 0 component in a singlet sigma state. And basically through that, it enables this purely electric quadrupole transition to kick in a transition in a 1.27 micron band. So this contribution can be accounted for, and we did. So basically, as you know, every rotational level of oxygen is split into 3 spin components, and each of these spin components have different contributions from this omega components of the sigma state. And you will see that this F2 component has only omega equal 1 contribution. So according to the theory, it should not really contribute to electric quadrupole transition at all. That's what we developed the model in 2010. So we just assumed that this component does not provide anything, and omega equal 1 components in F1 and 3 states also do not contribute. And these lines should be basically unobservable, the ones in red, because they're entirely between this F2 component. So, however, there was a later paper that thought that, okay, we are maybe not appreciating the contribution from singlet pi state, which is 60,000 wave numbers away. To me, it sounded ridiculous, but then after they pointed it out, we looked back at it, and now we're actually equipped with experimental spectra. So we created a new model, and basically this Q22 component is the one that corresponds to this transition between omega equals 0 component, and Q21 is the one that has this corresponds to admixture of the singlet pi state, which is really far above. And basically we recalculated everything. So now, but we felt okay. But if this is really true, maybe we can measure these transitions. And the group in Grenoble actually went back to the lab, and they did measure the super weak transitions, and we can. And this particular transition is a direct measure of this contribution from a far line electronic state. So we could really finalize our model, and then we had to introduce some correction factor to it too. But the thing is that that correction factor is basically just a polynomial. And at the beginning, we couldn't figure out what's going on based on just Grenoble data. And then when NIST data appeared, we could see that it's actually very smooth. So by just fitting this curve, we zero the residuals. And going back to the atmospheric spectrum, you can see that what we put in HITRAN 2020 based on this model provides substantially better residuals than HITRAN 2016. And this model is just basically based on purely NIST parameters and produces equivalent results, which is not surprised. Now, there is this collision-induced absorption that I mentioned, and you do see it in atmospheric spectrum, and it's actually quite appreciable in the 1.27 micron band, which we also have to account for. And moreover, for these different transitions between vibrational states of singlet delta and triplet sigma states, you don't really see magnetic dipole transitions well, but the collision-induced absorption is actually observable in the atmosphere. What is collision-induced absorption? I didn't mention. It's basically for homonuclear molecules like oxygen or nitrogen, they don't have permanent electric dipole moment. But when they collide with each other, they form this temporary collision complex that has a dipole moment. Oh, wow, okay. That absorbs. And basically that's, but when you do calculation, you have to remember that the collision can happen with different geometries, so you actually have to take all of it into account. And so the calculations are actually quite complicated. And in general, this collision-induced absorption is important for different atmospheres. And we updated recently thanks to Thijs Karman, who was visiting. And then we had Artem Finenko visiting us, who was calculating CH4N2 absorption. And it's important for atmosphere of Titan because the previous models had to do this correction factors. And this is a correction factor to correction factor basically here. And Artem did a new calculation which simulates the spectrum of Titan beautifully. And we didn't add it to HITRAN yet, but we've done this calculation. We are also working on adding the so-called planetary broadness to HITRAN to aid planetary atmospheres research. So you can see that for planets where different gases dominate, such as hydrogen or helium in the gas giants, or CO2 in Venus or Mars-like planets, the impact of pressure of these gases actually is observable in the spectrum, and we have to model it with different broadening parameters. And you can see the spectrum actually changes if you change the environment. And we collected a lot of this information from the literature and built semi-empirical models to populate the database. This is just an example again on how those models are built. I'm gonna skip some of the funny parts because I didn't realize with the time here, but I did want to mention that the molecules that sorry, the collisional partners that are in parentheses are those that are already in HITRAN. I'm just going to go through stuff quickly. So I did mention the absorption cross-sections for 300 molecules that we have. And again, it has very easy interface. And of course, some of those molecules are very important for terrestrial atmosphere to see how they contribute to the destruction of ozone layer and so forth. And of course, this is the type of molecules that we use to search for intelligent life in exoplanets. And these are the measurements at more extreme conditions, more relevant to planets, so either very hot or very cold atmospheres. Again, I did mention that we provide references for every parameter in HITRAN. So after you retrieve data, you actually offer this HTML file, but also the BibTeX file that you can use to cite not just HITRAN, but the original sources. And then you can have a mouse of the parameters, and then it can give you references. And we have a paper led by Francis Skinner that describes how we do it. How much time I have? 5 minutes? Okay. Yeah, I just very briefly mention about HITEMP, and I hope that at some point Robert Hargreaves, who works on it now, maybe he can give a talk more detailed about it at some point. But obviously for different hot atmospheres, we need high temperature spectra. And why HITRAN cannot accommodate it? Basically, you need substantially more transitions just through the Boltzmann population. Once you increase the temperature, a lot more energy levels are being populated, and it's you need to account for them. And this is a simulation. Basically, you can see it much better in this 3 micron band of methane. So you can see that at the beginning, everything started at the same place, but once you heat up, HITRAN is not adequate really anymore. It misses absorption substantially. So you really need this a lot of transitions that we provide in HITEMP. Just very briefly again, Rob put together the line list of methane, and it's based on this theoretical line list of ratio, which had 150 billion transitions. But we developed this sophisticated method how to reduce it to just 30 million transitions, which was a lot more manageable by radiative transfer codes. And Rob also compared against experimental spectra. You can see this is a line list that was previously used in a community ExaMol line list, which was a bit off when you compare with experiments. And then I was talking with astrophysics colleagues, and they said, well, why do you say that if experiment better simulates your line list, it is better? I was surprised by this question because to me it was obvious if you have well-controlled experimental conditions, then you can simulate the spectrum. That's basically ultimate truth. But unfortunately, this paper came out by Megan Tanek, which was looking at the brown dwarfs, and she was comparing different models and simulation of a brown dwarf, and you can see that our HITEMP line list basically is spot on the lines in the brown dwarfs. So we can get the confirmation from astrophysical spectra too. I know I'm really over time, so this is just overview of molecules that we have in HITRAN. Just to say that we are part of this Maestro opacity database, and we contribute to this project led by Nicole Lewis and Natasha Batalha, which will be run from NASA Ames. They already have a website. I don't think you can download data from there yet, but ultimately it's going to serve the GWST community with pre-calculated opacities. I probably am out of time. Yeah, I just 1 minute. Okay. I'll give you. I had some negative example, but I'll give you a positive example when the astronomer reach out to us. So sometimes there are some misconceptions about HITRAN, and there are certain errors being reported without alerting us, which turned out to be not errors. And then we have to write comments, ask people to write erratums. But the best approach to it is to contact us and see if something wrong. We can figure out what's wrong, and if not, we avoid extra embarrassment. This is a very positive example. Ashley Baker, who was measuring radial velocities of atmospheres, did in fact observe that the HITRAN 2016 provides some residuals in her spectra, and then she validated HITRAN 2020, which was better. And in fact, we were working together, and we already issued one update that's just substantial improvement even to that. So please, this is a really great example of collaborations. And we'll have HITRAN meeting here soon in June. And thanks to the HITRAN group. And thank you for your attention.
Thank you. You know, I must say that on hindsight, we should have given you 2 hours because you guys have so many things going on that, you know, it's a little bit unfair to try to make you fit everything in 1 hour. So with that said, questions, Igor?
Yeah, can I ask 2 short questions?
Of course.
Okay, 2 short questions. One, they're both related to astrophysics.
Okay.
The first one is about oxygen that you've shown.
Uh-huh.
So for you, it's like the ultimate goal is to model oxygen. For me, as a person doing spectroscopy, it's I need to get rid of it as a telluric band. So we noticed that when we tried to we used ESO models calculated with ESO SkyCalc. I have no idea what database they use for lines.
Yeah.
When we did the correction at the resolution of 20,000 spectral resolving power, everything worked fine. Once we went to R of 80,000, whatever we did, we couldn't actually correct the A band. There were substantial residuals. Do you think that this is related to the line shapes that are not properly modeled, or like it's on our end, like we don't model the line spread function correctly?
So it's basically both. So some of the models, including the ones that you mentioned, I don't know if they're updated, but they were using the outdated HITRAN. And again, this is a common thing in the telluric community that, for instance, SOFIA mission still uses HITRAN 2000, just because they have this hard-coded code. So it's something that we have to be aware about. But it is possible that there are something happening in the atmosphere that HITRAN cannot possibly help you with. There are winds, there are certain things that we don't have control of. So the best way to deal with it is basically empirically corrected. So start with HITRAN because it is based on the correct data. And it is better to use the more sophisticated line shape. And we do actually provide them for the A band. So you have to make sure your spectroscopy is the best. But then if you don't have, like they have in the stick-on spectra, certain measures taken to make sure they know actually temperatures and pressures above the spectrometer, then you can just add empirical corrections.
Okay, and the second question about stars. It's not about exoplanets, but it's about cool stars. The carbon stars, they're really notoriously hard to model. Mm-hmm. And so right now, if I take the state-of-the-art spectra in the near-infrared for like AGB stars, carbon and nitrogen enhanced or oxygen enhanced, they simply don't fit. I'm not talking about like 1%, I'm talking about 30%. So the spectrum itself will look like a noise, mm-hmm. like because it's like this. And the model would look like noise, but those will not be correlated at all. So when you try to fit one with another, it doesn't work. So have you tried validating your list for molecules, like in particular like CO and CO2, like the stuff that happens, and titanium dioxide, so the stuff that happens and appears in cool stars against spectra of cool stars?
So the simple answer is no, because but this is something we can consider. You can see that there are validations using brown dwarfs, and but we don't have titanium oxide and some of these extreme molecules. But CO we validate against the sun, so we do know that it's working pretty well. Yeah.
Right. So we have time for one more question. If there is more, no questions. Okay. The good thing is that Iouli is actually here, so now you know what is sitting on the first floor. So if you ever need a light list or you have any question about why your spectra doesn't fit, now you know who to go talk to. Thank you, Iouli.
Thank you. Yeah, thank you. Yeah. Yeah, no, but just mention it, like for HITEMP, but because we had this, slow calculation and stuff, which is kind of cool for mechanics, but we didn't have time.